start? Okay, sure. Just before I get started, just to double check if the audio and the video works. Can you see my screen? Okay, cool. Okay, all right. Yeah, again, thank you everyone for taking time joining us for the how to win a Kaggle computation part 4. So today we'll be talking about how to do model tuning. Okay, yeah, sounds good. Okay, so first of all, why model tuning? So basically, machine learning models, particularly the supervised learning models, they're trying to approximate real-life situations by learning from the limited data, which is our training data. And the way for a model to learn from the data can be changed by adjusting a few settings, so which are so-called hyperparameters. For instance, so the number of nodes of a decision tree, of the L1, L2 regularizations for linear regression. And so models can suffer from both overly simple settings, underfitting, high bias versus high variance, and overly complex settings, overfitting, which is no bias versus high variance. So what does that mean? So it may sound a little bit tricky for those who are not very familiar with those terminologies. So let's take a look at this picture, this diagram. So the way to read this diagram is so the horizontal axis indicates the complexity of the model from low to high, and the vertical axis indicated the error rate, right? So and the bias basically is the errors identified, observed again by comparing the predictions against the training data, and the variance is the error against the tested data. So as we can see from if we change the model, we train the model from several models from simple to complex, we would see the bias will always drop. The bias will always drop, but at one point, the variance, so the variance will drop as well, but at one point, the variance will increase. So which means so maybe in the model it's too complex and then too much information from the learning data, and by the end of the day we end up not being able to generalize the model, which means so okay, the model perfectly fits the training data, but we cannot use them to make any meaningful predictions on data, on the actual data or for the future. So that's the very fundamental concept for machine learning. I'm pretty sure most of you guys have been familiar with that. So the purpose of go back to our topic. So purpose of model tuning is to find a good balance between those two. So we don't want the model to be overly simple, or we don't want the model to be overly complex as well. So either way, they are not good. So okay, but so how to do a model tuning? I would say the validation, how to choose an appropriate validation strategy is the key to successful model tuning. So what are the validation strategies? And let's start from the very basic one. Let's say we have a data set with features which are the independent variables, and along with the target variable, sometimes we call it dependent variables. Either way, so we have a data to train the model with. However, if we use all the data to train the model, yes, we can do that, but we don't know how well the model will generalize when using the model to make predictions in the future. So therefore, a possible way is to split the data into one data set. One is called training, and then it's called validation. So typically we'll use 80-20 split. Sometimes people would use a 90-10 splitting. Well, there's no right or wrong. Yes, but the 2080 is probably the most common splitting numbers. Let's say so we split the data into a training and a validation. So we train the model using with the 80% of the data of the original data set, and then make predictions on the rest of the 20% of the data, which is our validation data set. So, and then compare the predicted value, against the actual dependent variables, and then we can get the we can calculate the metrics to say, okay, so how accurate the model is, or how much error we reduced. So we can use the different metrics to measure performance, but you got the idea. So we train a model, use a part of the data, then make prediction on the rest of the data, then compare the predictions against the ground truth, which is our original label. So this is a very naive way. So sometimes people just call it holdout validation, which means we hold out part of the data and using that data for validation. So that's the very naive way. But as you can imagine, so the way, regardless of how we choose the validation is that. So most of the time we'll just randomly sample it. But so the sample strategy is still arbitrary, right? So what if we just by chance sample too much, so too much positive samples in the validation set, then the actual proportion, and well, what I'm trying to say is, so the sampling or the splitting strategy comes with randomness, and the randomness could make the holdout, the single holdout strategy less stable. So therefore, people, if time allows, or so the resource allows, we would like to use a technique called k-fold cross-validation. What does that mean? So instead of using one holdout validation, one holdout data set for validation, we'll repeat it for k times. And in our case, so in this case, so we'll be using the 4 as a number to demonstrate the idea. So for the it's pretty similar to the naive holdout validation. So the difference is, so for fold 1, we keep the first 74% of the data as for training, and use the rest of 25% of the data for validation. And for fold 2, so we use the first let's say the first half of the data and the last quarter of the data for training, and use the third quarter of the data, third quarter of the data for validation, and so on and so forth. So by the end of the day, so we end up with 4 validation results, right? And then we will just simply average the validation result to get, so which will give us a more stable or more reliable validation result. So this is a very common way for validation to perform the validation. So, but sometimes, so let's say if we are working with a classification problem, and if by classification, I mean, so the dependent variable we need to predict is categorical, right? So it comes with many it comes from many classes, sometimes 2 classes, sometimes more than 2. And so one practical challenge is that how can we keep the training and the validation to make sure so both the training and the validation data set will have the same proportion in terms of the classes on the dependent variable. So what does that mean? So let's take a look at another technique, which is called stratified cross-validation. So it's very similar to k-fold cross-validation. The difference is that, so for training and the test of validation data set, we will keep the proportion of the classes the same as what is in the original data set. So in our case, so we have 20 balls. I'm pretty sure it's 20 balls. 20 balls in our data original data set, right? So and we have 15 red balls. And am I right? Oh, okay. So we have 1, 2, 3, 4. Okay, we have 12. We had 12. 1, 2. Anyway, 1, 2, 3, 4, 5. We had 12 red balls and 8. Yes, 12 or 8. 12 red balls and 8 blue balls in the original data set. So the proportion is 3 to 2, right? And so for each fold and for each training and the validated set, we'd like to keep the proportion of red balls versus the blue balls the same as what's in the original data set. And so we end up having 3 red balls and 2 blue balls for each of the validation data set. So that's so-called stratified cross-validation. So it works for classification problems, and so typically, so when we are working on classification problems, so we would like to use the stratified cross-validation for the validation strategy. Another interesting one is called k-fold group cross-validation. So it looks a little bit similar to the previous one, which is the stratified cross-validation. But here, the idea is so but for stratified cross-validation, we're talking about we're leveraging the target variable for our for sampling. But here for the group cross-validation, we are not using the target variable for data sampling. Instead, we will take a look at the so what's in the original data and see, okay, and trying to find that what are the most important grouping factor. For instance, when we were working on credit card transaction data, so we know we would like to group the credit card transactions from one card in either the training data or in the validation data set. So why we want to do that? That was because, so if we split the transaction from one customer in both training and validation, we can easily learn the information from training data set, and we sort of understand so the specific customer's behavior, and therefore the model is very easy to get a good result by making prediction for the customers we already know. But for other customers, so for customers that we haven't seen before in the training data set, so the model would become less accurate. So therefore, in order for us to get a more trustworthy validation result, we will want to keep the credit card transaction from one customer either in the training data set or in the validation data set. I noticed that there's a question. So Alpha said, is the size of the data set matter? Yes. So typically if the size is too small, so let's say if we only have a few hundred of samples, I suspect that the group cross-validation would work. So typically, so let's say if we're working on hundreds of thousands of samples, I wouldn't be worried too much. And in this case, in our case, you'll see, so the same color for the bars with the same color, they will be grouped. They will be split either in the training or in the data or in the validation. So we cannot split the bars with the same color and put them in both training and validation. So that's what is called group cross-validation. It typically it's I would say so. This is on the aware technique, because but generally speaking, most of the data sets we're working with, they would have some sort of so characteristics that if we train the model for a group of examples, and they may not generalize, and they may not work well for the other group of examples. So in that case, it would be nice to use a group cross-validation or group sampling. So for us to get a more reliable result. Next, we'll take a look at how to do validation for time series. So say we have this set from 2019, January 2019 to October 2019, and how can we do the validation? So we can do it in an iterative way. So let's say each time we would hold out a month of data and use the rest and use the fixed length of months of data for training. And so this is one method. Another way is so we would just moving the windows. Sorry, move the windows a little bit, and you can use 1 month of data for the first validation, and use 2 months of data for second validation, and they use 3 months of data for third validation, and correspondingly, so we would end up with less and less training data set. So I thought that either way comes with both the model A and the model B are not perfect, right? So it's just because the time series is so complicated and and very challenging for us to get a reliable validation result. But so personally, I find those two are more effective than other method I have tried. So I would encourage you to try both and find if you were to work on time series data, I would encourage you to try both and find out which one gives you the more reliable result, and then you can use it. So yeah, makes sense? Okay, let's move forward. So we've already talked about the key factors for model tuning, which is how to choose a appropriate validation strategy. But what is the challenge for model tuning? The biggest challenge for model tuning is that there are infinite number of combinations of parameters, the values for hyperparameters, but we only have limited computation resource. So therefore, it's just impossible for us to exhaust all the possible combinations. So how to efficiently and effectively find the optimal values for those hyperparameters is the foremost challenge for model tuning. And to this end, so people smart enough, they come up with some strategies. The most common way for finding the optimal values, parameter values, is called grid search. It's just so by name we know, so it's just this approach just tries to create grids by exhausting all different combinations, and you would iterate all the each of the possible combinations, and by the end of the day, so you would be able to tell which one works better. But Naturally, so you can imagine, realize that, so this is not very efficient, and I would say it's probably the worst strategy for finding optimal parameters. And the second way is called random search. So instead of so the exhausting all the combination, let's just random search it, and just randomly pick a value, and just go to next one. It may sound a little bit stupid, but it turned out to be a little bit more effective and a little bit more efficient than grid search. So apparently, so it's not perfect, right? But it works better than grid search. And third method is it's called greedy search. I will be covering it a little bit later. And third, the last one is Bayesian optimization, which is automated process for finding the optimal values for hyperparameters. So let's first of all take a quick look at what is a greedy search. So what it does is, first of all, it prioritizes hyperparameters based on the arbitrary importance, and which requires the good understanding about the algorithms, mechanism of each hyperparameters, and as well as the data. So, and still, so even you are very good at those concepts, those things. So you probably the importance of prioritization would still be arbitrary, right? But so regardless, so we would get a prioritized hyperparameters, and then we'll iterate every single hyperparameters and try to optimize it, try to test out it with the different values. And so we optimize one parameter at a time, and the iterative process until we optimize all the hyperparameters. So as you can imagine, this again, so this is not a perfect method, because it heavily depends on the path, or depends on the prioritization of the hyperparameters we arbitrarily come up with, right? So, and it doesn't take in account of the interactions of a parameter. For instance, so sometimes we have two parameters to control the model's complexity, and by when we tweak the one parameter to make the model more complex, but in the meantime, so another one, so another parameter tries to to make the model more simpler. So, and it's hard to tell so what would be the end effect, because one tries to go one direction, and then another tries to go a different direction, right? So, and the greedy search apparently doesn't take account of those kind of interactions. So, and which makes it again, so not a perfect method, but in my experience, it worked better than greedy search as well as the random search. But either way, so this is not the best way. So what is the state of art for parameter tuning, algorithm or method for parameter tuning? So this is a so-called Bayesian optimization. I would like to spend a little bit of time to talk about that, to talk about the Bayesian optimization, because it's such an interesting and effective algorithm. So I don't think we have enough time to dive into every single details, but hopefully I can just to give you some high-level ideas, so you can start using it instead of stuck into the technical details. Okay. It's pretty similar. So it's pretty similar to the supervised learning, where a model tries to fit a function y equals to a function of w and x, where x is the data and w is the parameters as opposed to hyperparameters of the model. In this case, so one algorithm we use commonly is called the gradient descent, right? So I don't want to spend time to explain that. I would assume so you already know what a gradient descent is, and so yeah. But if you don't know the details, it doesn't matter. So you just need to know. So as long as you know gradient descent is an algorithm for optimization, that's good enough. Okay, so gradient descent is used to find the optimal values for the parameters W that minimizes training errors. So this is what we would do for finding the best values for a supervised trained model, and which is also called the training process. But the way a model fits data is controlled by a set of hyperparameters H. So a model's performance can be expressed as a function of E equals to G. G is a function of H, which is the hyperparameters, and the X, which is the data. Where X, again, so where X is the data and H is the hyperparameters. But can we use the gradient descent to finding the optimal values for H, which is the hyperparameters? I pause it here a little bit for you guys to think about. So can we use the gradient descent to find the optimal values for H? So the answer is no, just because the so the performance function G of H and X is a black box. We don't know. For instance, so if we are going to train a logistic regression model, so we know the form of logistic regression, right? It's a well-defined form, and we even for the the neural network, we still know the form. We just don't know the the parameters, the values of parameters, right? So and which makes it so a little bit more well-defined optimization problem. But in our case, so in terms of training hyperparameters, so we don't know how the mechanics. We have some ideas on how those parameters impact the training, but we don't know how much and in which if there's a quantitative way for us to measure it, right? So essentially, so the function G of H and X is a black box, and we can't derivate it, and because we don't know the form, and there's no way for us to calculate the derivative, so therefore we cannot use gradient descent, right? So because the gradient descent depends on the derivations, and the third thing is also unlike the typical training process where it would be easier and less computation intensive to calculate the to calculate the metrics to do the gradient descent for every single iteration. But in our case, every time, in order for us to calculate to do a validation, if we try a different values for our hyperparameters, so it may take a few minutes to a few hours or even a few days to compute the validation result. So essentially, it's very expensive, and we don't have the luxury like what we would do for gradient descent to compute the metric, the cluster functions many times. And the last one is noisy. So there are lots of noises out there. So therefore, those four factors make the optimization of hyperparameter tunings, which makes the gradient descent not applicable for model hyperparameter tuning tasks. Okay, so make sense? I know so that this is could be a little bit tricky for some of you, but feel free to reach out to me, so to raise your questions if you have any. Okay, so this is when based on optimization to the rescue. Basically, it is a sequential design strategy for global optimization of black box functions that doesn't require derivative. So we'll take a look at take a little bit closer look at the algorithm and trying to find out what it actually does. So I would like to invite you to take a look at the diagram. This is a diagram. So the way to read it, so the horizontal axis is the value of hyperparameter. Let's say we need to tune one hyperparameter. Let's say the model we would like to tune only has one hyperparameter. And the horizontal axis indicate the value, the possible value on that hyperparameter. At that hyperparameter, we can think it as so the number of nodes for a decision tree, for instance. And the vertical axis is the value of the model's performance. Let's say accuracy. So for instance, we can train a model using different values of number of decision number of nodes for training a decision tree, and we would end up different accuracies, right? So that's the what is that's the y the vertical axis. So the dots are the observations we had, and in another word, so let's say here we have 3 dots, right? Which means we've already had 3 validations, and each validation we used a different value for a given hyperparameters. So we end up with 3 points. We end up with 3 points. And so here's the interesting thing. If we assume the function, the distribution of the model's performance is follows a Gaussian distribution, and we know when we've already had an observation, so we know the exact value. We know the exact value. So the possible the confidence interval will become much narrow on around that value, around a known observation, right? So which makes the confidence interval very narrow when we've already had an observation. But anything in between, we know, okay, we can assume, so they follow the value follows a Gaussian distribution, and anything. So if the value is further from a known observation, the confidence interval will become much wider, which means we have less confident. We have less confident in those areas, and it could become a little bit wider, or but we don't know. So, but the blue line, the solid line, is what we estimated based on the Bayesian theorem. So this is the blue line is the estimation of the model's performance. So this is a little bit of background about how we take a look at we can read this diagram. So here's the thing. If we already had 3 observations, we have 3 observations, and the question here is, how can we choose what would be the next value to observe? How can we choose the next value to train the model and do the validations, which will give us the most promising directions for us to get, to further improve the model? And it turns out that it becomes a problem. So some of you may be familiar with, which is the exploitation versus exploration trade-off problem. So what does that mean? So if we take a look at the left-hand side of the diagram, right? So when we had 3 points, right? And what we want to do is, first of all, from the exploitation perspective, right? So we would like to continue with the estimations, because the estimation is the, so based on what we've had from the 3 observations, the estimated value gives us a little bit of certainty about what we could expect, right? So, and we would go to the direction where it gives us the higher estimated value. So we would go to this one, so from here to here, so something in between. And in the meantime, so we would like to exploit a little bit, right? So, and it's just because, so when the value is close to, is near to the known observations, so we have less, we have more confidence. And in other words, so it's not very worth exploring from exploration perspective, because we would like to explore the wider, those unknowns, right? So, and in other words, we would like to explore those values where it gives us the highest, the highest, what is that? Confidence interval. And how can we balance it? We would use a sort of a called acquisition function to do the job, to make a good balance between the exploitation and the exploration, which I wouldn't spend, I wouldn't dive into the detail. But so the green area, or green noise, is actually the value from acquisition function. So in our case, so by having 3 observations, we know the next possible, the most promising value to go with is this one, the red none indicates, which gives us a good balance between the, so the exploitation versus the exploration. And therefore, next time, so we'll just use this value, this value, and to train the model again, and we end up with one more observations, and then we can repeat the process and again and again. So, and until we got the best set of value. So this is a so-called Bayesian optimization. Questions? Okay, so let's just move forward. So one question, so people ask, I've been asked often is, so given that, so we've already had an approach like Bayesian optimization, does that mean we don't even need to bother about the parameter tuning or model tuning? My answer is no. It's just because, so Bayesian optimization is a good approach, but it also has limitations. For instance, it's not able to deal with the categorical, if the hyperparameters, it's not continuous. If it's enumerate or categorical. So Bayesian optimization just it's just not able to deal with that. Another thing is, either way, sometimes the value, the range of the possible range for a hyperparameters may be very wide, right? So if we just leave and for the, in order to use the Bayesian optimization, we need to define a upper limit, and we need to define a range for each hyperparameters to explore with, right? So, but if we already had some prior knowledge on, so what is the reasonable range for one hyperparameter, so which will make the Bayesian optimizations more effectively. So therefore, so personally, I would use a sort of a hybrid approach, which combines the manual tuning, basically it's a graded search, and the automated tuning, Bayesian, which is the optimization. What I would do is I would probably start off by manually tuning each hyperparameters. So I would like to take a close look at the algorithm and trying to come up with some, some arbitrary importance for each one of the hyperparameters, and manually to one parameter at a time, and until I again use it, try to use the greatest search algorithm to tune the all the hyperparameters. So this way it will give me a sense of a good understanding about so what could be the possible range for each hyperparameter. And it turned out, so even by doing graded search, so instead of using Bayesian optimization, so the manual tuning used with graded search typically would give me a decent result, which is not the best, but it's definitely not the worst. And most of the time, it's an acceptable result. It will give me an acceptable result from the hyperparameter point of view. So, but having done the manual tuning, so I would use the Bayesian optimization to continue tuning the model, or in other words, fine-tune the model. And so just because, and it turned out so if we've already done the manual tuning, we've already had a range, we've already had a sense about so what could be the most optimal value for each individual parameter, and therefore we can come up with a range, a much fine-grained range for each individual hyperparameters, and we leverage this the result from manual tuning and using the result to put it into the Bayesian optimization, which will make the process much more efficient, and most of the time, so it will give me the better result instead of doing Bayesian optimization from scratch without having to do the graded search. So again, I would propose to use a manual tuning to tune each individual parameter, and then use the Bayesian optimization to further fine-tune the model. And we can definitely, of course, we can iterate the process. If we end up with after the Bayesian optimization, if we still have some doubts, and we can go back and manually tune it and iterate the process, and until we get the the best set of hyperparameters. So there's a question from the audience. So let me check it. So Xiao mentioned that, is there any circumstances that grid search might work better than Bayesian? Would this set size affect the choice of a hyperparameter tuning method? There are actually two questions. The first question, is there any circumstance that grid search might work better than Bayesian? I would say if the model is quite simple, and if the possible values, the range, the possible values for a hyperparameter is enumerated or categorical. So this is definitely some circumstances Bayesian optimization would not work well, or even not work, because one of the biggest assumption for Bayesian optimization is that the distribution of the value is and the distribution of the the model's performance, they both follow the Gaussian distribution. So if that's not the case, so for instance, so for what is that? Random forest. We know, so we can choose. There are two criteria for us to choose for tree splitting: entropy and Gini. So in that case, so Bayesian optimization just doesn't work, and we'll have to use either manual tuning or the grid search gradient search. But personally, I haven't done gradient search for a while, just because I find that, so personally, I find the manual tuning works better for me. And sometimes I even don't use Bayesian optimization, because so by manually tuning the model has already given me the quite decent result. So that's the first question. And second question, did set size affect the choice of a hyperparameters tuning method? Of course. Yeah. So again, so what we're trying to do is that we by giving the limited computation power or computation resource. Say if we can use the cloud service for the 20 hours to for the model tuning task, and so if this data size is quite large, yeah, and we definitely have to do something simpler than so Bayesian optimization, or if we can another way work around this to reduce the volume, reducing the volume of the samples, to reduce the size of sample data, and in trade-off time, so we can do more. We can experiment more iterations for Bayesian optimization, and in the hope that so we can get a better set of parameters. So yeah, there's no right or wrong, but to your question, yes, this set size does matter. Okay, no problem. Let's move on. So next, I'll be talking about the two popular algorithm, XGBoost and LightGBM. Oh, sorry, I forgot to mention that we decided to make a little bit adjustment about today's content, because I feel that so we probably don't have time to cover both the model tuning as well as the deep learning fundamentals. So we decided to just remove the deep learning part from this course, and we'll be focusing on the XGBoost and the LightGBM for the rest of the course. And if you are interested in deep learning, so hopefully CADASA can I believe we will be having some so deep learning focused learning opportunities in the future. Okay, so that's a side topic, and sorry for the confusions. And so let's go back to the topic. What is the XGBoost? XGBoost stands for Extreme Gradient Boosting. It is an implementation of gradient boosting machines created by Tianqi Chen, now with the contribution from many developers. And so I've also so included quite a few quotes from both the Kaggle community and the industry, and as well as so from the most of them from the Kaggle community. So as you can see, so it's a very powerful and I would say popular algorithm, particularly during 2015 and 2017. During that period of time, so many computation, in many of the computation, you can just simply use XGBoost without having to use other algorithm. In this way, you can just win the computations, and so I'm including those costs just trying to express that how popular and how powerful XGBoost is for so back to the time. But still, even for today, XGBoost, I personally find XGBoost and LightGBM are the most so two just my go-to choice. So if I would probably start when I was given any dataset, I would probably just use those two to test it out and to give me a so the baseline. So and then therefore and so I can make modification, or I can make improvements on top of that. But so anyway, XGBoost is one of the algorithm I'd really like to introduce to you guys. So what are the features? So I'll be briefly talking about the XGBoost features. So I will start from the theory part. One of the biggest difference between XGBoost, one of the biggest difference between XGBoost to the other, so conventional, traditional gradient boosting decision tree algorithm is that XGBoost uses a sort of a Taylor expansions for loss function approximation. I wouldn't dive into the mathematical details, but so what I'm trying to explain is to do is instead of explaining the mathematical details, so I just threw some iterations behind the scenes, so to help you have a basic understanding about what does that mean. So what does that? Why it's useful to use a Taylor expansion was that. So previously, let's think about for any specific machine learning task, we would like to define the object function, right? We'd like to define the object function. Then we'd like to come up with, we would like to come up with the optimization strategy. But here, in other words, so let's say if we were to use the same structure, XGBoost structure, gradient boosting structure for two tasks, one for regression and another for classification, we would have to write it twice. We would have to have two separate implementation just because of the difference on the loss function. Because of the, for regression and for classification, the loss functions, the form of loss function would be different. And therefore, we have to, even though we're using the same algorithm, but we have to write it differently. We have to write it differently and implement it differently, and which is painful. And also, it makes it harder to change the loss function or change the matrix. Change the matrix if we would like to implement something like early stopping. And given those engineering challenges, so using Taylor expansion allows us to customize our loss function. We don't have to worry about the implementation. We just need to define the loss function, and as long as the loss function is second order derivative, so therefore we can use it just one. We could just implement it once and decouple the loss function from the major algorithm. So that's one benefit. And the second benefit is that it enables customization. It allows the model to gather more information from the second order derivative to decide which directions to go. And in other words, in a simpler word, so it enhances the model's capacity to learn more information from the data. This is key for XGBoost to have a way better model performance than the previous gradient boosting decision tree implementations. And so these are the two. This is the first benefit, the features of XGBoost. And second one is the recognized learning objective. Most of the previous GBDT implementations, they don't include the recognizations into their learning objective. They just care about purely the loss. But XGBoost introduced the tree complexity as a separate recognition into the model, which enhances the models and the ability to to stabilize the model and increase the robustness. So that's a second feature. A third feature is parallel learning, which is an interesting one. It's not hard to imagine a bagging algorithm such as random forest to be parallelized, right? So parallel learning is not very challenging for it's not even for bagging algorithm. For instance, for random forest, right? So we know random forest tries to create many decision trees and then combine the results together, right? So that's the very simple way to describe random forest. And it's not hard to imagine that. So the parallelization will occur when we try to construct many decision trees, right? So for instance, one CPU can work with constructing decision trees, some decision trees, and then another CPU can work on constructing the other decision trees because they are independent. So yeah, it would be hard to parallelize the process. But for boosting algorithm, that it's tricky, right? So it's naively, so naturally, so I personally find I just do find that it's hard to imagine how boosting algorithm can be parallelized, because so the definition of boosting is that boosting algorithm will gradually improve the model by adding more and more decision tree to it, right? So one decision tree tries to minimize the error, the error residue between what the previous tree predicts versus the ground truth, right? So for instance, if we were to predict the person's age, right? And the ground truth there's the guy who's 20 years old, and we created a decision tree, and the decision tree predicts this guy's age is being 16. And for the second decision tree, instead of predicting the age being 20, it tries to predict the residue, which is 20 minus 16 equals to 4, right? So, and in other words, so every tree added to a boosting algorithm tries to minimize the losses between the previous tree prediction versus the ground truth. And so essentially, in a simpler word, so it depends. Every single decision tree in boosting depends on the previous trees. Depends on previous, and which makes it a sequential process, right? A sequential process. And previously, I found a hard time to imagine how that would work to parallelize the boosting algorithm. But it turned out, so for XGBoost and for the same thing for Light GPU, the parallelization was not done when the algorithm tries to construct a new trees. It occurs when the algorithm tries to find the optimal splitting point for every single feature. So here's the thing. So the parallelization, again, the parallelization occurred on the feature level, or on the column level, not on the tree level. So the algorithm tries to use the different multi-cores or CPU cores to find the optimal splitting point at the same time for one tree. And once it's finished so finding the optimal values, optimal splitting point, and finished the tree splitting, right? So and it moves to the next tree. So the process between constructing trees is not parallelized, right? But the process for finding the optimal splitting tree can be parallelized. So that's the key idea. So that's the very first time I've seen, so a boosting algorithm being parallelized. So, and which really made it, more efficient. And so there are a few other features like sparse aware implementation and out of call computing and handles missing values gracefully. So, but I wouldn't spend much time on those. They're relatively they're still nice, but so I think it's so we can just so skip them and without having to explain in details. But questions? Okay. So I will be using the XGBoost line example to explain how can we take a look at the parameters and how can we prioritize the parameters. So first of all, I would like to group the features, group the other hyperparameters into few groups. The first one, the first and the most important one is based on the idea that XGBoost is based on decision tree, right? So, and we know how the way to tune a decision tree is through controlling the complexity of the decision tree, right? And typically, the more complex a decision tree is, so the model is more capable to learn more information from the data. But in the meantime, the risk for the model to become overfitting increases. In other words, the more complex the tree is, the more likely it could go overfitting. But the less complex a tree is, so the less capable the model is, and but the risk for it to become underfitting increases. So again, so the purpose for us is to find a good balance, to find out, so the what is a good balance to make it not too simple and not too complex. And in that, to this end, so there are a few feature hyperparameters that we can deal with. The first one is the max depth, which is probably the most influential parameters for XGBoost, because it controls the overall complexity of the model. I just for each parameters, I just listed the default values and the typical and the range, the possible range and the typical values. And in our case, so max depth, the typical value is 3 to 10. But I would like to challenge you guys, every one of you, a question. So what is the typical? So if you have previous experience using other algorithm, decision tree-based algorithms, such as random forest. Okay, so what is the typical value for max depth in random forest? And what about naive decision tree? And the second question is why the difference? I would encourage you to think about that. So can any of you give me the answer? Okay, so Xiao Lei, give me an answer about the random forest is 15 to 30. Okay, anyone else? Any ideas? So I think, and the 12, so Xiao, you're right. So 15 to 30 is also my, so my the empirical, based on my empirical, my previous experience. I think this 15 to 30 is a reasonable range for random forest. But my next question is why? Why so even for the same decision tree model, or for the same decision for XGBoost and the random forest, they're both based on decision tree. But why we see the difference in terms of the typical values for max depth? Can anyone think of a reason about why? Okay, so I will explain, and just and here's my personal explanation. Shelley mentioned that because our random forest uses voting. So here's the thing. Bagging. Let's go back to the fundamental differences between bagging and the boosting. So for bagging, what we're trying to do is essentially we're trying to minimize the variance by bagging many decision trees together, by combining the predicate power of different decision trees, right? And in other words, if we take closer look at every single decision tree from random forest, they would be somehow outfitting, but we don't care. So because by making a model more complex, right? So we would reduce the bias, right? So we reduce the bias, but the variance become increases. How can we do that? We can use the bagging to reduce and mitigate the variance. So even though the model, every single model, every single decision tree within a random forest is overfitting, but by bagging them together, so we reduce the risk of overfitting by decreasing the variance. So this can be proved mathematically, but I don't think we have time to come up with the conclusion or to conduct the process. But here's the thing. So bagging, the biggest benefit for bagging is that by bagging, we can reduce the variance. And so therefore, when we train a random forest, we tend to encourage every single decision to be a little bit more complex, or a little bit overfitting. We don't care, right? But because so by the end of the day, so we would have other decision trees to help us reduce the variance. So that's why we see, so the typical value for max depth for random forest is way larger than what we can see from XGBoost. And in the meantime, boosting, the philosophy for boosting is, so we don't want to make mistakes, right? Every single time, we try to make a tiny little improvement, but we don't want to, to do it too much, right? So even though it's small, let's say if every time we get closer to the target a little bit and a little bit and a little bit, right? And essentially by making, so many smaller but less complex model, and even it's simple, right? So by then gradually adding those simple model to XGBoost or to any boosting algorithm, we're trying to every time. So the bottom line is every time for every single decision tree added to a boosting algorithm, so we would expect them to have a low variance. We don't care about the the bias, because by adding more and more trees into it, we would eventually reduce the bias. But we don't want them every single decision tree to increase the variance. That's why, so for boosting, so every single decision tree tend to be way less complex as compared to the so what could be in random forest. And interestingly enough, if you compare it to the so the max depth, if we train 3 models, the bagging, boosting, and the naive decision tree, you'll probably find, so if we tune the model to parameters, you probably find, so the decision tree in bagging is the most complex one, and the naive decision tree is in the middle, and the decision tree in a boosting algorithm is the least complex one. So that explains, that's how I interpret this difference in terms of the values, typical values on max depth between those algorithms. So the reason I brought it up is because this is so the difference between bagging and the boosting is a very frequent interview questions for machine learning interviews. But I find most of the people, and they just so overlook the point that the difference between bagging and the difference between bagging and the boosting in terms of how each algorithm impacts the the bias variance trade-off. Okay, so questions? Okay, all right, let's move on. Yeah, and thanks for Shelley's answer. Next one is next parameters we'll take a look at is called mean child weight. Basically, it behaves a little bit different for classification and regression problem, but we can simply think it as a number of leaves. A tree, a node, a leaf requires for splitting. Why would we need that? It's because so if we have no restrictions, right? So we would expect the decision tree to grow and grow and grow, and by the end of the day, we would end up with one sample on one node, which is not desirable, right? Which is not good, because we would like to if we make a split, we want to the node to be representative. We don't want to the node to be very, very specific to just a few of the examples. So this is another important parameters to control the complexity of the tree. Again, so I would like to throw another question, which is, so if we tune a model to this, let's say if we tune this parameter, and we against the sample this set with 1 million of samples, and let's say by the end of the day we say, okay, the best value for mean child weight is 30, and when we were to retrain the model against the production data, which contains, let's say, 100 million of samples, would that change? Would that value, would we need to change the value? Or should we still keep using the same value for mean child weight? I guess no change. So this is from alpha. It's hard to see. It's hard to say, just because so typically the retraining using against the production data is the last step, and typically we would trust the tuning result using the subsample. So this is what we have to do. But personally, I would increase when we moved from the experiment process to the production process, or model deployment process. And when we change the training data from 1 million samples to 100 million samples, I would tend to increase this value a little bit. And in other words, so I would like to, it's just because, so just think about that. So if we have 1 million samples, and we say, okay, in order for the tree to split, we want to at least 30 samples on a node. But all of a sudden, we proportionally increase the samples from 1 million to 100 million, right? So, and this value could change. The optimal values for mean child weight could change. But again, so this is some empirical trick. It's just because it's really hard to verify it, to validate it on a larger data set. But I have done some experiments on this side. So my tip is that, so if we were to do the similar thing from so we train a model using a smaller data set and productionize it using against a really large data set, we probably need to tweak some parameters just because of the size. Some models, they don't care much about some models and some hyperparameters, they're not very sensitive to the size of the data, but some parameters they are sensitive to the size, and mean child weight is just one of them. Okay. I saw there's another questions from Alpha. Is there any process for that? Can you elaborate a little bit more? So what is the process that you're referring to? Okay. Yeah, so feel free to take your time to, okay, changing the size of mean child weight. No, I mean, so here's the thing. So a typical process of a data science project is that, so we probably want to use a subsample, a small sample of the data to test out, to do some experiments, right? And create a POC and tune a model, find the best parameters. And once we finalize the process, and we probably want to use the most current data, and which is typically larger than the data set we used for experimenting. And therefore, we need to retrain the model using the parameters we tune against a smaller data set. And because of the difference between the two data sets, one is the experiment data set is smaller than the actual production data sets. So we probably need to tweak some of the parameters just because of the difference of the size, data set size. But that's not always the case. It's just so I would rather to see it as a question for you guys to think about than giving you a conclusively saying, okay, this is something you have to do. This is what I mean, or this is what I wasn't what I was trying to do. So again, so what I'm trying to do is so to throw some questions to you guys and for you guys to think about, and just so this to do some exercise. To do something exciting, but instead of drawing and conclusion. Okay, makes sense? Okay. The third parameter is called gamma. It's a minimal loss reduction required to make a further partition on leaf node of the tree. The larger gamma is, the more conservative the algorithm will be. So to be specific, this loss reduction is the sum of the values of the second deviation. But so if you not very familiar with the algorithms, I would suggest you to use a mean child weight, to tune mean child weight only. But if you are more familiar with the the algorithm, I would say personally I find the tuning gamma is more effective. It's more effective than tuning mean child weight. So just based on my experience. But feel free to use one of them to tune. If you were to tune XGBoost model, because they're doing pretty much the same task by controlling the model's complexity. They are secondly to, in terms of the importance, I would still say that is the most important from the tree complexity point controlling perspective. But the other two, the mean child weight, gamma, there's still some parameters I would like to tune with. We talked about the the XGBoost from the decision tree perspective, and the second aspect I would like to talk is from the stochastic process point of view. It was from the idea of boosting, because by boosting, so we know every time we would like to use a different model. We'd like to train the model with a different version of data. And by different version of data, we're talking about two things: different examples and different features, right? And this is why we would want to have two parameters to the following two parameters, which are sub-example and column example by tree. And both of them, the range for both of them are from 0 to 1, indicating how much percentage of the data we would like to include to train a new decision tree. And by sub-example, we mean the sub-example controls how much percentage of examples, and the column example by tree controls how much percent of the column example by tree. And similarly to the previous slide. So I also have two questions for you. Actually, they are the same question. So for instance, for sub-example, if we tune the parameter, this parameter, and we end up with 0.3 being the best value for this parameter, what could it be? What could it indicate? What's the indication? And what we need to do for next? Can anyone from you give me share your thoughts? Alan Song mentioned, so increase tree depth. Okay. We can reduce the regular, from Shelley, we can reduce the regularization factor. Okay, that's another way. Okay, so I have tips. So let's think about the data. So we have one of the common sense for training for machine learning on this sense is that the more data, the better, the merrier, right? So, but here, keep in mind that the sub-example controls the percentage of examples we want to use for training a new decision tree during the boosting process, right? And if the value is 0.3, which means so the model, we find that every time so we only need 30% of example to train new model, to train new decision tree. That will give us the best result. What's the indication? Indication, so it's just in my opinion, the indication is that there's something wrong with the data. There's something wrong with the data in terms of the examples. And some examples, they're less predictive or less valuable than other examples. Maybe there are lots of nuances noisy, there are lots of noisy examples in the data set, right? Which confuse the model by, so if we include those noisy examples into the model could, so become worse. The model's performance becomes worse by, so using the model, train the model on the other data set. So that could be an indication on, so the, data quality in terms of examples. And similarly, if we saw the tuned values for economism by tree is a smaller value, which may indicate there are some noisy features in the data set. And what we need to do is, okay, so we probably need to apply some feature selections and to make sure we have the most useful and the most representative features. So that's so how we, that's what I'm saying. So model tuning is like a black art, right? So, and sometimes when we are talking about the model tuning, we're not only talking about the tuning itself. The tuning result can be used for us to come up with more ideas and more insight about the data and the problem. And this two are good examples of explaining, so how we can leverage the tuning result to help us examine the data quality, right? And another side side note is that, so if we included, if the data set, the features contain many sparse, if we have sparse features in the data set, by sparse features, example of sparse feature could be one-hot encoding, the result from one-hot encoding, or from TF-IDF encoding. So if we have sparse features in our data set, the columns by tree could be a very, very small values. I've even seen, so it depends on the, how many of them in the data set. For instance, so if we have, so the 10 dense variables, dense numerical variables, but in the meantime, we have 10,000 sparse features. So as we can imagine, the dense features or the sparse features, they are less informative. It's not saying it's not. It doesn't necessarily mean that they are not useful. It's just they are not very informative, and we still need to use them. We still want to use them. It's just from the model perspective, we want to so to decrease to use a smaller value for economism by tree, because so every time, so we probably just want to include so the 10 dense numerical feature and a couple of the sparse features. So, and in that case, the economism by tree could be very small. Okay, so let's move forward. The last aspect I'd like to talk about for XGBoost is the relationship interaction between learning rate versus the number of rounds. So first of all, let's take a look at the parameters of number of rounds. So number of rounds is very similar to the idea of the concept of APOC in deep learning training or training deep neural network or training, so even logistic regression or linear regression. It just means that, so how many times we need to repeat the in neural network. The concept of APOC is the number of times so we would like to repeat the optimization process. But here, so the number of rounds just simply equals to the number of decision trees we would like to use. We'd like to train for XGBoost. So typically, so the larger is the number is, so the model the model becomes more complex, right? So, and we would expect to see the bias decreases. But again, so by making the model more and more complex, so the model can become too complex and become overfitting. And on the right-hand side, I just included a diagram to demonstrate the relationship between the number of round versus the the validation score from the validation score on the validation data set. And in our case, the metric is log loss. So for log loss, the less the better, the less the better. So as you can see, so when we increase the number of rounds from so 1 to maybe 200 to 50, so we see a very sharp drop in terms of the test error, test log loss, which means that the model learns very fast by adding decision trees up to let's say 100. But after 100, it becomes much smoother and much smoother. And maybe after, in our case, so the best number of round, it turns out that the best number of round is 250. But how can we find that 250, right? So if we train a model one time, train a model, let's say train the model again, you use 100 and train the model again and use 200 and train the model again and use 300, which is not ideal, right? So because, so if we've already trained the model for 100 times, and if we already added 100 decision tree to the model, why can't we just continue training it, right? And therefore, so a very useful technique is, which is called early stopping, can be used to help us determine the best number of rounds. And what it does is, so instead of finish the training and do the validation, so it does the validation on the fly. So every time, so we added a new decision tree to the boosting algorithm, such as XGBoost. So we would like to validate it against a predefined validation data set and monitor the model's performance in real time on the fly, right? So, and if we observed that so after many times, if we added too many a given number of decision trees to the model, and we still didn't observe any improvements, then we will stop the training process, right? And we will take a look at the historical training history and find the best number of round. So this is the technique called early stopping, and it's quite useful for both training training XGBoost the algorithm, as well as the training. You probably see it quite often in training neural networks, but so for XGBoost, we do have the similar concept. However, the best number for the best number of round depends on other factors, and particularly depends on the ETA, which is also called learning rate. So by learning rate, you can take it as a step size, right? So if you imagine, so you're running a sprint, right? So and every time your step size is 3 meters, you probably need 30 steps to finish the 100 meters of run. But your step size is 5 meters, you probably just need 20 steps to finish the running. So, and the learning rate indicates how fast do we want the model to learn. And if it's too large, for a larger learning rate, so the model converges faster, or learns faster, but the accuracy becomes the model's performance may suffer from underfitting. But if we use a smaller learning rate, so the accuracy could be better. The model's performance could be better. However, so it may take a longer time to finish the training process, to finish the training or for the model to converge. So therefore, in practice, one useful trick is that so we can use a larger learning rate, say 0.1, to tune other parameters. And once we get the other parameters tuned, we can switch gear back to a smaller learning rate, which, for instance, 0.01, to finally train the model to finally train the model for a better accuracy. So that's a very common and useful trick for training XGBoost model. So again, we would use the larger learning rate to tune other parameters, and then go back to a smaller learning rate for a better accuracy. So yeah, so that's for XGBoost. And next, I will spend a little bit of time talking about the LightGBM. So LightGBM is a very similar algorithm as XGBoost. I would call it the enhanced or evolved version of XGBoost. So in fact, so it has become my powerhouse for pretty much my machine learning works, and except for so the image and the text. So for those texts, I would use deep learning. But for pretty much so other tabular-ish data, I would just use LightGBM or XGBoost, and mostly use with LightGBM. And the biggest benefit for LightGBM is the speed. It's probably 4 to 7 times faster than XGBoost with the comparable parameters of comparable settings. So I explain a little bit about why it's so fast. But here, so I also include some background. It's Microsoft's DMTK project, and it's developed by the winning team of DD Data Science Computations in 2017, if I wasn't wrong. So here's a few differences between LightGBM and XGBoost. First of all, XGBoost is and the other GBDT algorithm. They're using a sort of a level-wise tree growth. What does that mean? So every time, so it tries to to make a split by level by level. So, and it will iterate the process and until you find the best splitting. But on the other hand, LightGBM tries to split regardless, it doesn't care about I need to be careful. It does care, but let's just put it for a little bit for a while. Let's say LightGBM less concerned about the level, but it concerns about what is the best direction, right? If it requires, let's just make splitting on this branch and over, okay, and which makes more sense, right? Because so typically, let's say, most of the time the data naively are not uniformly distributed, right? So we could have we have more populations in California than in other states in United States, right? So, and if we create a model, to train a model for United States, sort of property market, right? So we probably have more examples in California than in other states, right? So, and in California, so the situation could be more complicated than the United States, right? And which makes sense to have more splitting, more branches in California than in other states, right? So, and naively, I would think, so the leaf-wise tree growth makes more sense. And in fact, this is probably the biggest reason for LightGBM to have a better model performance in some of the tasks than XGBoost. And another difference, a major difference between XGBoost. Oh, so go back to the previous slide. So I forgot to mention one thing. So because of the difference, so for XGBoost, we care the very first parameters we like to tune is the max depth. But for LightGBM, we would like to tune the model starting from the number of leaves, just because both of the models has the biggest impact on the decision trees complexities. So another major difference between XGBoost and LightGBM is so LightGBM was if I recall it correctly, was the very first time. So we used the approximation, histogram approximation for instead of exact search. What does that mean? So let's imagine we are working on this set. We're working on this set with with a feature called income. We call it income. So income could range from $0 to, let's say, $1 million, right? So and we have 1.2 million of samples from Calgary. And what could be the unique values of income? It could be, okay, so it could be few thousands, let's say 5,000. We have 5,000 unique income values. We have 5,000 unique values on the income feature, right? So, and in order for a decision tree to find the best splitting point, so it will have to iterate through all the 5,000 possible values, unique values, to find out, okay, so at which point we can make the best splitting, right? So in other words, so we need to do the experiment. We need to calculate the iterate 5,000 times to find out the best splitting point. However, if we histogram, we discretize the data, the income data, and instead of using the 5,000 exact value, let's use 100 bins or 100 histograms to represent the data, right? So, and it's probably not a bad idea, right? Because most of the time, so who cares the $5 difference between, so if we saw the an income value is 100K and this is 100K and 5. So who cares the difference, right? So it would make more sense to instead of using the exact value, let's use the so the discretized value for to represent the data. And in that case, so we will only need to iterate 100 times, which is the number of histograms or bins we decide to use to represent the data, right? So, and all of a sudden, so the complexity decreased from, not complexity, the workload, the number of iterations decreased from 5,000 to 100, right? Which is a significant improvement. And that's probably the biggest improvement on LightGBM. And after LightGBM introduced such an idea, and so the XGBoost just followed the step. And for the modern version, for the newer version of XGBoost, you will see there's a parameter called tree method. It can choose to use exact, which tries to find the best splitting point by using the exact value. And if we choose to use a histone or GPU histogram, so which means so instead of using the exact value, we want to use the so histograms for approximation. So this is something that significantly simplifies the simplifies the computation complexity. Okay, so that's another difference between LightGBM and the XGBoost. Okay, here's so just like similar to as what we have last week. So I just put together a chart to demonstrate so the with the different techniques. So how we would see the progress on leaderboard in terms of the improvements of the model. So recall last week, so after adding the magic feature, we end up with 0.5124, which is approximately top 10 solution. And by top 10, I mean, so it's already, so by achieving top 10, so you would get a bronze medal in this case. And so after, and I also added the three, there are the three. So by manually to the model, so we could end up with, we could have ended up with a top 8 solution. And if we choose to use Bayesian optimization for automated tuning, so we would end up with the top 6%. And if we tune the model using Bayesian optimization, and plus we decrease the learning rate from 0.5 to 0.0 or 0.1. So we would further improve the model, and which is equivalent to a top 5 solution. And by top 5, so you could have achieved the silver medal. So as you can see, so we can see that so the progressive improvements by using a different techniques and tricks, and so which allow us to continuously improve our model. So just to wrap up, so the purpose of model tuning is to find out the optimal values of hyperparameters, so that the model can be of a good balance between underfitting and overfitting. So that's the purpose. So again, so the purpose is to find a good balance between less complex model and too complex model. So that's the purpose of model tuning. And validation strategy is a key. If we didn't do the validation, didn't choose the model validation strategy well enough, so the more we tune the model, and the end result may be worse, right? It's just so and the validation, if the validation failed, right? So, and which means so the model is less likely to work well in the future. That's why, so it's very important. It's critical to plan ahead and carefully choose the validation strategies ahead of time. So next, automated tuning based on information is a powerful method, but it can be more powerful by combining prior human being knowledge and through manual tuning. And XGBoost and LightGBM are the state-of-the-art algorithms for most of the tabular dataset except for text and images. So that's pretty much what I have today. Next, I'll just walk you guys through the notebook we have. Sorry, I've had some hard time with the Kaggle notebook because it timed out, it kept timing me out for the past a few days, so I was not able to finish the running of the notebook on Kaggle notebook. But I decided to just upload the to send the notebook directly. But here's the thing, until this part, previously, so until the model tuning, the notebook is exactly the same as what we had last week. And from now on, the model tuning part, so you will see the new contents. So here, I just demonstrated so how to do the manual tuning in a graded search way, and then use the BSL optimization for automated tuning, and then we can we can just so change the learning rate from 0.5 to 0.01, and then retrain the model. So you would notice the difference. So using the smaller learning rate, we can get a better result, but in the meantime, it takes a longer time to train the model. So that's pretty much all that I have today. So I think we still have a few minutes. So I would, so if you have any questions on today's content, so I'd love to address that. This is one trend. So one way of model tuning I use is to train models on training data and validation on the data set. After finding a good enough model, e.g. number of rounds equals to 100, I train the model on the whole data set and then apply the final trained model to unseen data in the future. Is my approach correct? Do I need to adjust the number of rounds when I train the model on the whole data set? That's a very good question. So my gut tells me that. So, well, again, number of rounds is pretty similar to the number of leaves. So we talked about. So again, so it controls the complexity of the model, right? In short, so number of rounds also has some effect on the model's complexity. Given that, so you train the model, the value of 100 was from the experimentation of tuning against a smaller data set, but the actual data set is way larger, and which means that there could be more scenarios or more complexities in the larger data set. I would suspect that if you probably need to increase the number of rounds a bit more, and to take account of the new complexities introduced by the larger data set. But I don't have a good answer because I can't. This is something. If you don't do the validation on the actual data set, so you cannot prove it. You cannot. So, what I would like to suggest is if you have enough computation power and time, if time or resource allows, you can do the experiment, right? So you've already had the training example, right? So you end up with the 100 being the best value for number of rounds, right? So using a smaller data set, you can do the same thing. You can repeat the same tuning process, but this time against the larger data set on the production data. So just do the experiment and see if 100 still holds the truth. And if it not, but I would suspect so this time, so you probably end up with a larger number than 100. But I could be wrong. So but the only way to prove it is to do the experiment. So I would encourage you to do the experiment to see the result, to test it out. Okay, so any other questions? Use hyper-opt to do BSM optimization. That's the same thing. So optimization and the BSM optimization. So which is what I used in this notebook. They are just different implementations of BSM optimization. So I think they will just both work well. But I personally I don't have much experience with hyper opt, but so I would expect they are the same thing. Okay, if there's no further questions, I'll just wrap up today's session. And thank you so much again for taking your precious time on the weekend to attend our session. So I truly appreciate it. And yeah, I believe so. The TAs, my focus from CADASA will be sending out the material slides and as well as the notebooks to you guys. So if you have any questions, feel free to reach out to me through Slack, so from WeChat. So I'll be there. Okay, thanks so much. Have a good weekend. Bye bye.